So 8.4 is our word problem section. So we'll start off. If you want to follow along, we're looking at page 424 to start us out. So some real world problems. Building something. Bridge truss. A section of a bridge truss design is shown. Find the total length of the beams required to build the section to the nearest tenth of a meter. So, first of all, everything that is in gray, I don't know why they put that in there just to confuse you, but it is not part of it. So we're only looking at this blue section here. So basically what's asking for is our materials person is going out to buy material. We need to know how much beam we need. So what's the total length of all of those lines? So first of all, how many lines do we have? So we've got 3 triangles, but 2 lines are doubled up to the triangle. So we're not going to count those twice. So we need to know what we have. So we're adding up all the different line segments. And second, we need to know how we're going to name them. So we can't just call them little b, little a, little c, because unless we're looking at the triangles individually, because b is one angle, or it is actually multiple angles because we've got multiple triangles, but they're all going to be called b. So we can't be using some of the, we have to be more specific in our naming. So we're going to use 2 and 3 number naming. So we're going to call this line segment is AC. This angle isn't just A, it is CAB. Because we've got 3 B angles, we've got ABC, CBD, and DBE. So 1, 2, 3 angles. So we have to think about how things are named in something like this. So in the end, we want to add up all of our line segments. So I'm going to start by just writing them out to make sure that I've got them all. So my first triangle is AC, CB, and AB. So I've got those 3 written out. So I don't need to do CB again for my second triangle. So I do have CD and DB or BD. Doesn't matter which one goes first. So now I've got those 2 lines. So again, I don't need to do BD again. I just have DE and BE. So 2, 4, 6, 7. 1, 2, 3, 4, 5, 6, 7. If you count them all out, making sure that you've got them all. So I'm going to leave that up in the corner so I know. The only one that I do know so far is AB is 6.2. So let's find some other ones. How are we going to do that? Let's look at this, think about it for a while. What can you use? So we have our little hint up here. We have a right angle triangle. So we can go back into chapter 7 for this one and start looking at our right angle, or use our right angles, SOHCAHTOA trigonometric ratios for this one. So basically these tools that we have, if we've got a 90 degrees, we can use SOHCAHTOA, we can use sine law, and we can use cosine law. Those are our 3 weapons. And cosine law has an angle formula, and it has a sine formula or side formula. As long as you remember one of those, you can figure out what the other one is. So we're going to start off by finding two of these lines by just using our trigonometric ratios. So let's label them first. So if that's my 90 degree is angle C or ACB, then directly across from it is my hypotenuse. I have angle A or angle CAB right now. So I'm going to say that CB is the opposite and AC is the adjacent. So if I want to find my adjacent, let's do opposite first. If I want to do my opposite, if I want to find my opposite angle, angle CB, I'm going to use sine of 37 degrees equals opposite over hypotenuse. Sine equals opposite over hypotenuse. So my opposite is what I'm trying to find over 6.2. I can rearrange my formula. 6.2 sine of 37 degrees equals my opposite angle, which is angle CB, or sorry, not angle side CB. And that all works out to my opposite angle. Actually, I'm going to switch. Oh, it's too big. So CB, or my opposite side, equals approximately, since we're rounding to a tenth, is 3.7. So I know in here is 3.7. The opposite. So now I've got some information in here because I've got these little lines here. And what that means is that this is an equilateral triangle. All three of those are going to be the same length. So I can just copy in. We can use some other math to figure that out, but we can also just copy that in, that those three are exactly the same. So then I know that CD not U, BC are all exactly the same. So that makes this a little bit easier. So now I want to know my adjacent side. And two ways I can do that. I've got a right angle triangle, which means that I can use Pythagorean's theorem. I've got two sides. I can figure out the other side using so something else in our a squared plus b squared equals the hypotenuse squared is the Pythagorean theorem, is also something we can use for solving triangles. I think I'm going to use cosine, though, because I feel like that might be a little bit easier to do than Pythagorean's theorem. So I'm going to go with cosine of 37 degrees equals the adjacent. In this case, the adjacent is AC over my hypotenuse. I could also use tan now that I've got my opposite and my adjacent. Could have used tan, but we're going to stick. It's always best to go back with the information that they gave you in case you made a mistake in your first section. So almost exactly the same, this time with cos of 37. So you see those two look quite alike. And that rounds to approximately 5.0. meters. So now I've got 5.0 being AC. All right, so now I just need to figure out my last triangle. Only I don't have much information about my last triangle. All I've got is that it is got one side that's 3.7. So now I need to start playing with my angles to figure out what that is going to be. So we need to know a little bit about triangles for this to make sense. So one thing we need to know about triangles is that they all add up to 180 degrees. So now I know in my first triangle, ABC, that I've got 90 degrees and I've got 37 degrees. So if I do 180 minus 90 minus 37, I can figure out pretty quickly that that last angle, let's change colors so you can see, is 53 degrees. Now I also know something about my middle triangle. My middle triangle has 3 equal sides. It's an equilateral triangle, which means it also has 3 equal angles, which means 180 divided by 3 is 60 degrees. So we've got 3 60-degree angles on this one. Now we also know a straight line is 180 degrees. Again, so 180 degrees minus 60 degrees for this one, and 53 degrees for this one, means that our last angle B is 67 degrees. So now I've got one side and one angle. So I still need some more information. So think about this one. One other thing we know, we don't have a right angle triangle, but we do have an isosceles triangle. We do have one with 2 equal sides, which means it also has 2 equal angles. So I know this is 67 degrees. I know this is 67 degrees. So I can also find my third angle, 46 degrees. So now I've got a lot of information to work with. So now I go back up to my ideas. I can't use Pythagorean theorem because I only have one of the sides. I can't use SOHCAHTOA because I don't have a 90-degree angle. So now I'm looking at sine law and cosine law. So I always want to use sine law over cosine law. I could probably use either right now and figure it out. Actually, no, I couldn't because I need to have 2 sides to use cosine law. So, but sine law is always easier than cosine law. So if you can use it, always do it. So I can use it because I have an angle with its opposite side. So that gives me something to compare anything off of. So what I'm trying to find is a side. Either side, they're going to be the same because their opposite angles are the same. And because they've got those little hashtags telling me that they're same. So I want to put the side on top. So let's choose DE is what I'm trying to find. Its opposite is the sine of 67 degrees. So again, I want to put the angle on the bottom because they want to match. And I know that 46 is opposite to 3.7. So DE equals, I can move sine of 67 over. and multiply both sides by it to get it on the other side. Then I've got some calculator work to work through. So I'm rounding, and I've been asked to round to the 10th place, which means to 1 decimal place. And I've got a length of 4.7. And since these are equilaterals, I know that they're both going to be 4.7. So now it's just a matter of adding up all 7 sides, which I get a length of 31.7 meters. .7. So we need 31.7 meters of beam to build this truss. So this was a pretty complicated question. We need to start off by realizing what information we have. We needed to know a lot about remembering from grade 6, 7, 8, the ideas behind equilateral and isosceles triangles. Isosceles having 2 equal sides, 2 equal angles, and equilaterals having 3 equal sides, 3 equals angles. So start off by knowing what information or which strategy we're going to use. We're going to throw in, if we've got a right angle, we can use SOHCAHTOA or Pythagorean's theorem. If we don't, we can use sine law and cosine law. Just going to save this because it keeps going down on me. Come on. Next slide. Nope, next slide. All right, so we've got what was in, so the solution that was in the textbook. You can flip through the PowerPoint that's on Classroom. And I've got all of the writing out of the answers and their information about what they said. Okay, example 2 is find the height of a cliff shown to the nearest meter. So the height of the cliff. So the height of the cliff is AB. So that's what we're looking for. So again, we've got a right angle to play with, which is great. In one of our triangles, make sure we don't make the mistake by thinking that it's in both, because it's not. We can find the third angle of the bottom triangle. So it's kind of nice just to start off with easy information. What have we got? We can easily find, we've got 2 angles, we can, on each one, we can find the other angles to get us started if we think that might help. But again, we've got a right angle, so we can go, maybe SOHCAHTOA will help us. Maybe Pythagorean's theorem will help us. We also have sine law we can play with. And we also have cosine law. So these are some of the things that can get us started in there. So take a look. So the first thing we can do kind of is figure out what this third angle is. 180 degrees minus 62 minus 50 equals 68. We got a 68-degree angle here. So really what we want to know is about the right angle, but we need to use the bottom triangle to figure that out. So the most important line in this section is here. So I can't use SOHCAHTOA or Pythagorean's theorem on this bottom triangle because it's not a right angle triangle. Oops, now you want to switch. But I can use sine law because I now have two opposites that I can play with. I want to be able to find CB, or little d, as we can call it, because it's opposite an angle called big D. So I want to find a side. So I'm going to put that side up first in my sine law, because the top left is where you want to put where something that you're looking for is. Then the sine of its opposite angle, side 50. So I want to play with the opposites. The ones that I have has a distance of 160 and a angle of 68. So again, divide or multiply by sine 50 on both sides to move it to the other side. Oops, my eyes are getting bad tonight. 68. And by the magic of our calculators, we'll find out that side D, or side BC if we want to call it, so CB equals D, if that doesn't confuse you, is approximately 132 meters. We are working in meters. So it says rounded to the nearest meter, so we can start off by doing that. So now we have the knowledge that our bottom triangle, or our bottom, and we can redraw this as well. We've got a right angle there. We know that you're 138. We know you're 33. We know you're 90 degrees. That is all the information that we have here. So we have a 33 degrees. Now I'm going to go up to SOHCAHTOA and Pythagorean theorem because I know I've got a right angle, so I can use both of those. So let's label it. Opposite the right angle is the hypotenuse. Opposite the angle that we want is our opposite angle, and so that makes 138, the one closest to it, the adjacent angle. So what can I use? I want the opposite, and I have the adjacent, which means I need tan. So tan of any theta equals the opposite angle over the adjacent angle. So tan of 33 degrees equals my opposite, which in this case is AB, or I could also call it little c, since this is opposite big C, over top of my adjacent angle, which is 132. Multiply both sides by 132 to make it, to get it over to the other side, equals AB. So AB is approximately 86 meters. And again, I do use this type of math quite a bit for measuring really tall items, figuring out what the angles are, and then making triangles. Things that are too big to be measured by any other means. So now, AB is what I'm trying to find at the end. The height is 86 meters, and we've got it. It's a little bit easier than our first example. So again, we found the degree, we found the length of that adjoining line, rebuilt it again, and then used tan. So when solving problems involving right angles, you can apply the primary trigonometric ratios, which is SOHCAHTOA. Primary trigonometric ratios is the big fancy math words for SOHCAHTOA. When solving problems involving acute triangles, so again, we are only dealing in triangles that are acute, that have angles under 90 degrees. You can apply the sine law or cosine law. So those right angles, you're not applying sine law or cosine law. They needs to be acute angles right now. Use the sine law if you're given an angle on the opposite side, plus one other side or angle. Use the cosine law if you're given two sides and the contained angle or all three sides. So visually you can look at the problem and know which one you're going to have. If you ever have the three sides given you, so you've got information, I should put in, if you're given a triangle and you've got 6, 7, 8, they've given you the three numbers, you only have three sides and no angles, you know it's going to be cosine law. The only time you can use sine law is if you have two opposites. So you've got an opposite pair, and then you've got the opposite of what you're trying to find. So whether that's they give you this side and you're trying to find the angle, or they give you the angle and you're trying to find the side. Did I say the same thing twice? They give you the side and trying to find the angle, or give you the angle trying to find the side. You have to have one opposite pair. So cosine law, that's not a right angle. If you are given the middle one, so again, visually, if you are given kind of a middle angle between two sides, then you're also looking at a cosine law, where it's that you have to use cosine. So you're not given, you don't have any opposites that you can play with that you can use the sine law from. You've got one of each. So if this was A, you've got little a, but not big A. If this was B, you've got big B, but not little b. Oh, I already used you. And if you're C, you've got little c, but not big C. So you've got one of each, then you're using cosine. If you've got a pair, big B, little b, what begins with B, then you can use that. So sometimes when I just look, or every time, if I just look at the problem with it being drawn out, I can see which one I'm going to end up using. Because either I have a right angle, and I'm going to go back to SOHCAHTOA, or I've got an opposite section that I can draw on, or I've got one of each of the pairings. And then I know if I'm going to go with SOHCAHTOA, if I'm going to go with sine law, or I'm going to go with cosine law. A number of problems involving trigonometry require multiple steps. Look for techniques and make connections to other branches of mathematics such as geometry in order to solve the problems effectively. So we do need to know equilateral triangles are all equal sides, all equal angles. Isosceles triangles, you don't need to know the names, but the ones, some of them have two equal sides. If it has two equal sides, then it also has two equal angles. And they're the ones that aren't touching each other. So if these two are equal, then not the one in the middle of the two of the lines that are touching each other, but the other two are the same. All right, again, actually, do I have a problem? Look for practice problems. I'm not sure if I put them up today.